This lecture is on chapter 1.1 and 1.2. 1.1 talks about matter, which falls into two categories, pure substances and mixtures. We'll talk about those when we get there. And then we're going to be starting to talk about measurements and measurement systems. So we're going to be talking about the metric system, also known as the SI, or System International System. And the metric system is a base prefix unit system. So we'll talk about both the base units and the prefixes. And then we'll finish off with temperature. Okay, first we have matter. What is matter? Well, we can think of that as anything that has mass and occupies space. It might be easiest to think in terms of solids, liquids, and gases. Everything that we normally think of shows up in one of those three states. There's actually a fourth phase, and that would be plasma, but that would be like in the corona of a star. Not a very common phase of matter. Actually, fire also has plasma, but that's not really something that we normally think of when we think of matter. Pretty much the only place you can get away from matter would be in a hard vacuum, such as in interstellar space. Okay, well, matter itself can be classified into two categories. We have pure substances and we have mixtures. Pure substances have a fixed composition, and no matter where you would find them, they're going to have that fixed composition, which is in contrast to mixtures, which essentially you can have varying proportions. The easiest way to think of that is varying concentrations. We'll talk about more in a bit. Okay, pure substances. We have two examples of pure substances. We have elements, and so carbon all by itself will be an example of an element. The oxygen that we're breathing is an example of an element. The nitrogen, the main gas that we're breathing, is an example of an element. And elements essentially can't be broken down into two or more simpler chemicals. Meaning like if we take carbon dioxide, we can break that down into carbon and oxygen, but not an individual element. Now, we do need to learn about the elements and the element symbols. I would point out that all of our elemental symbols are a 1 or 2 letter abbreviation. And we need to make sure that the first is always uppercase and the second is always lowercase. There's a big difference between big C, little u, I see one element, versus big C, big U, I see two elements there. And so we need to be case sensitive. If you're used to writing everything in uppercase or lowercase, you're going to have to change your ways. Okay, well, we don't need to know all of the element symbols. We only need to know about a third of them. And by far the most common are the first 20. So we need to know the first 20 elements, and that would begin with hydrogen and helium. Then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. To the next row we have sodium and magnesium. Sodium is Na. Then aluminum, silicon, phosphorus, sulfur, chlorine, and argon. By the way, argon is our third most abundant gas in the atmosphere. Going down to the next row, which we're going to find are called periods, we begin with elements 19 and 20, potassium and calcium. Again, by far, these are the most common elements. Okay, now we can skip over to elements 24 through 30. That's chromium, manganese, iron, cobalt, nickel, copper, and zinc. Then 33 through 36 for arsenic, selenium, bromine, and krypton. Let's go to the next row with rubidium and strontium, elements 37 and 38. We can now jump over to elements 47 and 48 for silver and gold. Ag is argentium. Argentina is named after this metal, and a lot of silver was mined in Argentina. Then on to 50, and Sn is 10. On to 53 and 54 for iodine and xenon. Okay, to the next row for 55 and 56 for cesium and barium. Let's jump to 78 through 80 for platinum, gold, and mercury. Now, do note where gold is. Right above that is silver, and right above that is copper. That might help you remember who's who: copper, silver, and gold, and that's the value of our coinage metals. Let's jump to 82 for lead. And that's the last one that we really need to know the elemental symbols for. In another class or in another date, you might want to know uranium and plutonium, elements 92 and 94, but for right now, this is what we need to know. You might want to get your own periodic table out and mark this to illustrate these same elements and start putting some effort into learning these symbols for these names, because soon you're going to be given element names or compound names, and we need to know what symbols are they representing. Okay, back to compounds, where compounds are the other type of pure substances, and compounds have a fixed composition as well. So for example, water is always H2O no matter where you get it. From the deepest ocean, from an ancient ice body, from a flying by comet, it's always going to be H2O. So what if you have H3O? Then it's not water. Okay, then on to mixtures, and mixtures are significantly different than pure compounds or pure substances in the respect that they can have varying proportions. Again, the easiest way to think of that is they can have different concentrations. So you might think of a mixture of salt and water, which can have different concentrations of the salt to the water. Now, we have several types of mixtures, and the first is what are called homogeneous mixtures, and that means the same part. Solutions are examples of homogeneous mixtures, and essentially if you took a drop of water and brought out a magnifying glass, of a solution, you wouldn't be able to see a difference between one part and another. You can break out the best microscope and you're not going to see one difference between one portion and another. We'd actually have to get down to the atomic/molecular level before we would see, okay, here's a water molecule and here's a sugar molecule or a sodium ion or whatever is in solution. Okay, we also have heterogeneous mixtures, and hetero means different. So here we have different parts, and the easiest way to spot a heterogeneous mixture is it would be opaque, because the different parts are going to scatter light. Actually, milk, while we're told is homogeneous, is actually not homogeneous, it's homogenized, where they break up the milk droplets to be very, 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 very small so that they stay evenly distributed. But it scatters light because we have the oil droplet phase, we have the protein solid phase, and we have the aqueous liquid water-based phase. Okay, on to measurements, and we have two measurement systems that we're going to be talking about, the metric system and the English system. By far, science is dominated by the metric system, and as you get to learn about the metric system, it makes a lot of sense. It's easy to use, and so we'll see why it dominates science. Now, when it comes to measurements, essentially a measurement is essentially the comparison of a known standard to what it is you're trying to measure. So maybe I want to measure the length of a piece of paper. Well, I'm going to line it up with a measurement device like a ruler or a yardstick or a meter stick, and from there essentially measure off my value. So again, all measurements are a comparison of your unknown, what you want to know, to a known standard. That's usually your tool. So here we have a graduated cylinder, and we put our unknown liquid in there and line it, and essentially use these hash marks, these lines, to help us see what is that value. So we have a known value, in this case of 900 and 1,000 milliliters, and then these hash marks in between, giving us some indication as to what values are going to be in between those big numbers. Okay, so again, comparison of our known to an unknown. Let's see, what is our known here? Well, it's hard to see with an electronic balance, but if I brought out the classic balance, oh yeah, that's right. We might put a stone's weight in one and get our stone's weight in grain in the other. So essentially, we're comparing our known to an unknown. Okay, all of our, like I said, the majority of our scientific measurements are done using the International System of Units, or the Système International, the SI system. And essentially, this is pretty much the metric system, only it includes other units like hertz and volts and a bunch of others. But essentially, it's based on the same prefix, the same prefixes, I should say. Okay, so talking about the metric system, it is a base unit, a prefix-based unit system, and so it all begins with the base unit, which describes a fundamental quantity. And so the base unit of length is the meter, represented by the lowercase m, liter, represented by the uppercase L, grams, lowercase g, and those are the main ones that we'll be working with. I would point out that the established base unit for time is seconds, and for temperature is Celsius, same as centigrade. Essentially, they're both the same. We'll talk more about them in a little bit when we talk about temperature and temperature conversions. Okay, so these are the base units, and then are going to come in the prefixes. Well, what are the prefixes there for? Well, they are there because maybe the base unit is too big or too small, and so it may be beneficial to subdivide it into smaller quantities or get multiples, meaning bigger quantities. Okay, now when it comes to the prefixes, we usually don't relate one directly to another unless we're involved in a direct measurement. So here we can see that on that meter stick, we see each of those numbers is a centimeter, and that there's 10 hash marks in between each, and each of those would be a millimeter. So we might, when we're making a direct measurement, relate millimeters to centimeters. We normally don't want to do that when we are performing calculations. Now, when we're making calculations, what we want to do is we want to learn what are the adjustments of each prefix to the base unit. And the nice thing about this is they're all adjusting the base unit by some nice easy factor of 10. So for example, a kilo is 1,000. Doesn't matter which you attach that kilo to, it's always 1,000. So a kilometer is 1,000 meters, a kiloliter 1,000 liters, a kilogram 1,000 grams. And if I had a kilo inch, what would that be? 1,000 inches. So no, that's not a normal unit, but the point of the matter is a kilo attached to anything is going to be 1,000. Okay, we need to know these prefixes, and so in this chart we see the larger values at the top and the smaller values at the bottom. And so right in the middle we have the base unit, and so that means that everybody on the top is getting bigger and bigger and bigger, and everyone below it is getting smaller and smaller and smaller. Now do note the pattern. We have deca, 10 to the 1, hecto, 10 to the 2, kilo, 10 to the 3, and then we jump to mega, 10 to the 6, giga, 10 to the 9th. And so essentially we go 1, 2, 3, and then jump by factors of 3, so 10 to the 6, 10 to the 9, 10 to the 12, 10 to the 15. And then we have the same in the opposite direction. Deci, 10 to the negative 1, centi, 10 to the negative 2, milli, 10 to the negative 3, and then micros, 10 to the negative 6, nano is 10 to the negative 9, and they would continue in that fashion, so 10 to the negative 12, 10 to the negative 15. And we're not going to learn what those other ones are, but essentially they would then all be some nice easy factor of 3. I'm pointing this out because it might make it easier is, say, in the case we are trying to determine what this prefix value is, and we're thinking it might be 10 to the 5th, that doesn't match the pattern, and so that might help us to essentially reduce down the possible numbers that we need to remember. Now, I do want to point out that these exponential numbers are the adjustment to the base unit. So 1 giga anything is 10 to the 9th of those anything. So 1 gigameter to the 9th meters. A gigabyte, 10 to the 9th byte. What we're going to find is our prefix unit is always going to get a 1, and our base 10 number always goes with the base unit. Hopefully that'll be easy to remember. The base 10 number always goes where? With the base unit. That's going to be a question that we need to start asking and answering ourselves. Now, I know that a lot of people have learned how to convert within the metric system already. Well, if you have and you are very confident in it and you know that you're competent in it, then you don't need to worry about changing your ways to do things my way. I'm just trying to show you a way that avoids most of the most common mistakes. The most common by far is to remember the right numbers and then put it with the wrong units. But we're going to not make that mistake because we're going to know the base 10 number always goes where? With the base unit. Okay, so again, you don't have to reinvent the wheel if you've already mastered this, but if you haven't mastered this, you probably want to start doing it this way. Okay, we do need to boil this down to the abbreviations, and do note that they are case sensitive. We have a capital M for mega and a lowercase m for milli. Don't confuse those, so we need to be case sensitive. And we need to know these base 10 adjustments, so eventually we need to get this into our memory. Okay, let's do an example, and this is going to introduce you to the unit analyses technique, which actually is going to be showing up in a future lecture. I believe it's our next lecture, but I want to go ahead and show you it in action, and then we'll actually formally go through the steps in that technique. Okay, so we're asked to convert 37,400 nanometers to micrometers. First thing is step one, and we want step one to be nice and easy. What are we after? And let's write it down on the far right. We're after micrometers, and micro is that backward looking Y guy. That's the Greek letter mu. Okay, then step one tells us a lot about step two. If we're after a single unit, then we're going to start with a number with a single unit. Well, there's only one of those given, so we're starting with that 37,400 nanometers. Do note, step one fell into our lap, step two fell into our lap as well. That's nice. Essentially, no real head scratching so far. Then, the beginning of step three always is nice and easy as well. Let's place the unit that we start with across the denominator line. We know that anything divided by itself is 1, and hence it cancels. And now, what does it take us into? Well, we would ask, can we go straight from nanometers to micrometers? And the way that I'm teaching this, the answer is no. We have to go through the base unit. So first into meters. Why the base unit? Because all of those prefixes related directly to the base unit. We don't have conversion factors for millis to centis, etc. And if we did, we'd end up with 100 of them. And we don't need 100 if we can get away with 10. Okay, we're not after meters, so let's place meters across the denominator line. And do note, the previous step prepared us for this step. And now we ask the same question. Can we go from meters to micrometers? And now the answer is yes. And at this point, our setup is done. If all of our units cancel but the one that we're after, we know that we've done this correctly. The only thing that we can do wrong is to put the wrong numbers in or push the wrong buttons on our calculator. Alright, now we're going to bring in the numbers, and we need to remember the base 10 number always goes where? With the base unit. So the tens go with the meters, the nanos, the micros, the kilos, the gigas, all of those prefixes get a 1. And now 1 nanometer, like 1 nano anything, would be 10 to the negative 9th. Whereas 1 micrometer, like 1 micro anything, is 10 to the negative 6. And eventually you need to know these numbers. Okay, I have 3 significant figures in my original number, so I'm going to have 3 in my final answer, so 3.74 times 10 to something. My original number was 3.74 times 10 to the 4. And now that all of my numbers are in exponential form, with the exception of the 3.74, remember when numbers in exponential form are multiplied, those exponents are added. And when those exponents are divided, they are subtracted. So again, we have 3.74 times 10 to the positive 4 plus negative 9 minus negative 6. And again, numbers in exponential form when multiplied, the exponents are added. When divided, those exponents are subtracted. Do you have to do this way? No, you can always use a calculator, but I find I'm less likely to make a mistake with the signs of numbers and adding them together than I am with putting numbers on my calculator. You're always welcome to use your calculator, but this essentially would be the easy way if you didn't have your calculator. Okay, on to the next example. We want to convert 0.0072 kilograms to milligrams. Alright, we're using our unit analysis techniques. Step 1, we're after milligrams. Step 2, we're starting our calculation with that given number of kilograms. Again, step 1 and step 2 drop right into our lap. On to step 3, let's get out of that initial unit. Now, can we go straight from kilograms to milligrams? No. To go from one prefix unit to another, we have to go through the base unit. In this case, grams. We're always guaranteed we can get into the base unit, and for the same reason we're guaranteed we can get out of that base unit. And so in this simple fashion, we've manipulated our units to get it to our answer. That's really what unit analysis is manipulating your units that set up your problems for you. And I'll give you this simple 4-step procedure in our next lecture. Okay, and then the numbers, and the base 10 number always goes where? With the base unit. So the grams are our base unit now, and the kilo is going to get a 1, The milli is going to get a 1, and a kilogram, like a kilo anything, we've already seen is 10 to the third, and a milligram, like a milli anything, is 10 to the negative third. Okay, I have two significant figures in my original number, so 7.2 times 10 to something. My original number was 7.2 times 10 to the negative 3. Negative 3 plus positive 3 is 0. 0 minus negative 3. Remember, when you subtract a negative, it becomes positive. So we're back to positive 3. Again, you can always use your calculator if this doesn't work for you. Okay, on to temperature. And first, what is temperature? Well, we can think of temperature as saying how hot or how cold something is. But what does that mean? Well, as I have here, it's a reflection of your thermal energy or heat energy. Heat is actually a form of energy. But what does that mean? Well, actually, temperature is not the same as energy, but it's related to energy. So, for example, I would point out I can have a cup full of boiling water and a lake full of frozen water, and the lake has much more energy than the cup because there's so much more of it. And I can stick my hands into a 454-degree oven to pull out the Thanksgiving turkey. Of course, I have oven mitts on my hands, but my arms were bare. Can I stick my hand in 212-degree boiling water to pull out the noodles? No, that's not going to be so nice. Why can I stick my hand in a 454-degree oven, but not into the 212-degree water? And it's because water holds so much more energy per temperature unit than the air does. So we see that the energy relationship to temperature is based on your subject, are we talking about air or water, and how much is there of it, a cup versus a lake. Okay, so then what is temperature? Well, temperature is actually a reflection of the motion of your subject particles. So, for example, anything cold enough is going to have our atoms right up against each other, and there will be no motion at all. At this point, we have what's called zero absolute temperature, or 0 kelvins. Kelvins is our absolute temperature scale. So then, as we would have some motion, a little bit of twisting and turning and vibrating, we would essentially be developing temperature. So temperature does take up position in different types of motion. Twisting and turning and vibrating is one type, and then straight line motion would be another. And I think we know that as you get to higher and higher and higher temperatures, you'll go from a solid to a liquid. And then we have free motion amongst your particles. And then with high enough temperatures, they'll go to a gas. And at that point, they've gone into straight line motion. We'll talk more about gases at a later time. Okay, so let's talk about the Kelvin scale. And when we would have 0 kelvins, we have 0 motion, 0 temperature. And I would point out then we can't have negative kelvins. That's kind of like saying you're going slower than stopped. Okay, there's also this Celsius scale, also known as the centigrade, centi as in 100 grade scale. And this is where we have 100 gradations or 100 temperature units between the freezing point of water and the boiling point of water. Boiling point of water at 1 atmosphere, meaning sea level. Okay, there's one more scale, and this is actually the very first scale, was the Fahrenheit scale. Where Fahrenheit wasn't a scientist, he was an instrument maker, and he was trying to come up with an instrument to measure temperature, but he needed to put some type of a scale on there, and so he got a very heavy brine solution, so he had a lot of dissolved solutes, and got it as cold as he could get it, and he called that 0 degrees F. And then he got it, before it froze, that is, and then got it as hot as he could get it before it boiled, and he called that 250 degrees F. Well, what that leaves us with is for pure water freezes at 32 degrees F, I imagine you know that, and boils at 212 degrees F. And again, your boiling point would depend on the atmospheric pressure. We'll talk about more about that in the chapter on gases. Okay, we do need to learn to convert between these different systems, and first, in my mind's eye, whenever I'm converting between any system, I see this picture that you see before you. And this shows that there are two things we need to take into account. Do note we have different starting points. Where we have the freezing point of water, we have 0 degrees C, but we have 273 kelvins. And we have 32 degrees F. So when we're going to have to take that into account when we're converting between these three systems. Okay, then note the different sizes of our temperature units. Between freezing and boiling, we have 100 degrees C, but we have 180 degrees F, so we'll have to take that into account as well. Note, we also have 100 Kelvin, so the Kelvin temperature unit is the same size as the centigrade/Celsius degree unit, but they have different starting points. Again, we'll see that we have to take these two things into account for any conversion between two systems. Okay, let's talk about converting between Fahrenheit and centigrade. And so when we're doing so, we have to take into account that different starting point. So that means we're going to either add or subtract 32 degrees F. Again, we're taking into account our different starting points, so we're either adding or subtracting 32 degrees F. If I start in degree C, nope, freezing point is 0. We need to get up to 32, so that means we would be adding 32 degrees F. When I'm in degrees F, to get from freezing point 32 down to 0, I would be subtracting 32 degrees F. Now we can just figure this out on the fly if we see this picture in our mind's eye, telling us that we have to take into account that different starting point. Then we have to take into account the different size temperature units. And that means we're either multiplying by 100 degrees C over 180 degrees F or 180 degrees F over 100 degrees C. We'll know which of those we're doing at the time. Okay, so which are we doing first? Well, it depends on where you start. If we're going from degree C to degrees F, we first have to get into degrees F before we can add or subtract that 32 degrees F. We can't add or subtract unlike units, so that's why we had to first convert from degree C into degrees F. Then we can add or subtract the 32, and if we were in centigrade, we would be at 0. To get it up to 32, we would add the 32. So I hope we can remember to essentially determine that on our own when we get there. Now if we're going the other way, we started in degrees F, and so that's our opportunity to then add or subtract that 32 degrees F. So we pretend we're at the freezing point of water, 32 degrees F. What should it be in centigrade? 0. How do we get from 32 to 0? By subtracting the 32 degrees F. Then we're going to multiply by 100 degrees C over 180 degrees F. Actually, you should hit equals first, because your calculator will follow the order of operations, and we want to take that temperature, subtract the 32, get that answer, and then multiply by the 100 degrees C over the 180 degrees F. And if you remember something about 5/9 and 9/5, well, 180 over 100 is 9/5, and 100 over 180 is 5/9. Okay, so here's an example to convert 34 degrees C into Fahrenheit. We would first convert from degrees C into Fahrenheit. Then, now that we're in Fahrenheit, we add the 32 degrees F. And in this case, we don't have to worry about the order of operations. Putting this on our calculator, we should come up with 93.2 degrees F. Okay, now if we're going from degrees F, so let's say we have 55 degrees Fahrenheit, we want to know what is this in centigrade. Well, starting in degrees F, it's time for us to add or subtract that 32 degrees F. And we pretend we're at freezing point of water. That would be 32 degrees F. We need to get it to what in centigrade? 0. So that tells us we would have to subtract the 32 to go down to 0. All right, hit equals when you're done subtracting the 32, and then multiply by the 100 degrees C over the 180 degrees F. And when you hit equals, you should come up with 12.8 degrees C. Now the most common calculation that we're going to have in this class between temperature units is actually going to be between degrees C and kelvins. So what's the temperature, we're going to do one more example. What's the temperature in Celsius when it's 75 degrees Fahrenheit? And now, step 1, what are we after? The temperature in Celsius, so degrees C. Step 2, what do you start with? Well, of course, that's the given 75 degrees F. And now, is it time to add or subtract the 32 degrees F? That's the first question we want to ask ourselves. So it's a little bit different than our normal unit analyses where we would put F on the bottom. Okay, and yes, we're in F, so it's time to add or subtract the 32. So is it add or subtract? So we go to the freezing point of water, which is 32 degrees F. What's it in degrees C? Well, that would be 0. So to get from 32 to 0, we're going to subtract the 32 degrees F. Then it equals. Then, out of degrees F and into degrees C, and between freezing and boiling of water, we have 100 degrees C and 180 degrees F. So that's what those numbers are. If you want to remember 5/9, that's up to you. I'd remember the difference between freezing and boiling for C and F. When I put this on my calculator, I come up with 24 degrees C. So now we know what room temperature is in degrees C. Okay, now what's the temperature in Fahrenheit when it's 35 degrees Celsius? Well, still step 1, what are we after? Degrees F. Step 2, what do we start with? The 35 degrees C. And now now, is it time to add or subtract the 32 degrees F? No, we can only do that if we're in degrees F. So that means it's time to go from degrees C to degrees F. Then we add or subtract the 32 degrees F, and it would be add. Remember, we go to the freezing point of water in C, which is 0. To get up to 32 in F, we're adding the 32. Okay, so 35 times 180, divide 100, add 32, and it equals for 95 degrees F. As I was mentioning a moment ago, most of our temperature conversions are between kelvins and centigrade, and we're going to do something very similar. We have two things to take into account: different starting points. Where we're at freezing point of water, we have 0 degrees C, which is 273 kelvins. So that means we're adding or subtracting the 273 kelvins. And by the way, it's just kelvins, not degrees Kelvin. Okay, so if we're converting from degrees C to kelvins, we're first going to get out of degrees C and into kelvins. 100 degrees C under 100 kelvins. And then, now that we're in kelvins, we would add the 273. If we're going the other way, we're going to start with kelvins, so it's time to add or subtract the 273. And we would go to the freezing point of water in kelvins, that's 273. To get down to 0 in degrees C, we're going to subtract the 273. So again, very similar questions that we're asking ourselves. And then multiply by the 100 degrees C over the 100 kelvins. Let's do an example. What's the temperature in kelvins when it's 35 degrees C? And again, we can see we have different starting points and the same size temperature units. Okay, still, step 1, we're after kelvins. Step 2, we're going to start with that given 35 degrees C. And then, the time to add or subtract that 273 kelvins. No, we need to be in kelvins first. So out of degrees C and into kelvins. Now we can add or subtract the 273. So which is it? Add or subtract? Well, the freezing point in degrees C is 0, in K it's 273, so I think that tells us we're adding the 273. 35 plus 273, we really didn't need to do times 100 divide 100, we get 308 kelvins. Now, most people would simply add or subtract the 273 and mentally change the units from degrees C to kelvins. I don't know of any time this has really been a problem for anybody, but normally if you take care of your units, they'll take care of you. If you get sloppy with your units, then everything's off the table. But I don't know anybody that's ever gone awry by simply adding or subtracting the 273. Okay, let's practice some of the things that we've just learned. We're asked to convert 0.0849 milliliters to microliters. Well, step 1, what are we after? Microliters. Step 2, what are we going to start the calculation with? Well, that would be the given number of milliliters. The only number given has a single unit, must be what you start with. You gotta love it when it's a no-brainer. It's gotta be this. And then, step 3, let's get out of that initial unit, so out of milliliters. And now comes the big question. Can we go straight from milliliters to microliters? No, we have to go through the base unit, liters. Then from liters we can go anywhere else we wish, including microliters. Now remember, the most common mistake that students make when converting in the metric system is put the right numbers with the wrong units, and we're going to avoid that by remembering the base 10 number always goes where? With the base unit. And so the liters get the tens, the micros and nanos, the millis, whatever, get a 1. And 1 milliliter, like 1 milli anything, is 10 to the negative third, whereas 1 microliter, like 1 micro anything, is 10 to the negative 6. I have 3 significant figures in my original number, so I'm going to have 3 in my final answer. So 8.49 times 10 to something. My original number is 8.49 times 10 to the negative 2. Negative 2 plus negative 3 is negative 5. Negative 5 minus negative 6, remember that becomes plus 6. Negative 5 plus 6, isn't that the same as 6 minus 5? Or 8.49 times 10 to the 1. And we do need to get used to putting our answers in scientific notation and with the correct number of significant figures. Okay, we're asked to convert 4,712 kilobytes to megabytes. Well, again, we're using our units. Step 1, what are we after? Megabytes. Do note, that's the capital M. Step 2, what are we starting the calculation with? The given number of kilobytes. And now on to the beginning of step 3. Let's get out of that initial unit. So out of kilobytes. And then comes the big question, can we go straight from kilobytes to megabytes? No, we have to go through the base unit, which in this case is bytes. Then from our base unit we can go anywhere we wish, including megabytes. Okay, now for the numbers. The base 10 number always goes where? With the base unit. So that would be the bytes. Then the kilos, the nanos, the megas, etc. get a 1. And a kilobyte, 10 to the third bytes, whereas a megabyte, 10 to the 6 bytes. Now, before I put this on my calculator, I would point out that if you're trying to go straight from kilobytes to megabytes, how much are you really saving yourself? Just a little bit of chicken scratching, not a whole lot. And yet you're probably going to put a lot of burden up in the gray matter. So I'm not sure that's a wise choice, because there's always a combination of what you do with the hand and what you do with the head. You want to relieve some of the work on the hand, you're putting it in the head. It's probably wisest to do the other way and relieve some of the work to the head by putting it in the hand. Okay, we have 4 significant figures in our final answer. So 4.712 times 10 to the something. And our original number would be 4.712 times 10 to the 3. And then the 3 plus the 3 minus the 6. Well, 3 plus 3 is 6. Minus the 6 gives us 0. Now, to put in scientific notation, you do need to put the times 10 to the 0. Okay, what is the temperature in Celsius when it's 105 degrees Fahrenheit? Okay, we still have our normal step 1 equals degrees C. And our normal step 2, what do we start with? You know it, 105 degrees F. And now, is it time to add or subtract the 32 degrees F? We always start with asking about the adding or subtracting, because if we start in F, then we know it's time to add or subtract the degrees F. If we start in C, we know, nope, it's time to first convert into F. So, which is it, add or subtract? Again, you would pretend you're at the freezing point of water in F, which is 32, to get to the freezing point of water in C, which is 0, or subtracting the 32 degrees F. Note how we can think our way through this. If you want to remember an equation, that's up to you, but this process essentially replaces that need. Now, out of degrees F and into degree C, and the difference in freezing point in degree C is 100 degrees, in F it's 180. So 105 minus 32, hit equals, times 100, divide the 180, and I come up with 41 degrees C. Next, what is the temperature in Celsius when it's 235 kelvins? Okay, still using our units, still same step 1 and 2. Step 1, we're after degrees C. Step 2, we're starting with the 235 kelvins. And now, is it time to add or subtract the 273 kelvins? Yes, it's time to add or subtract the 273 kelvins because we're in kelvins. So which is it, add or subtract? Well, if I'm in kelvins at freezing point of water, that would be 273. To get to 0 in C, we're subtracting the 273. Most folks would just stop right there and just mentally change the units. If we want to take care of our units, then out of K and in degree C with 100 degrees C over 100 K. And like I said, most students don't do this, and I really don't know if it ever biting anybody on the butt. And that would be negative 38 degrees C. One of the things I want us to eventually start asking ourselves is, does our answer make sense? Because if that had been a negative temperature in kelvins, would that have made sense? No. And so often we can catch mistakes by simply asking, does our answer make sense? Okay, we just finished chapter 1.1 through 1.2, beginning with types of matter, which fall into pure substances, elements and compounds, and mixtures. Then we have measurements and measurement systems, and we spent some time learning about the SI system, same thing with a metric system, a base prefix unit system, so we learned about the base units and we learned about the prefixes. We finished off by learning about temperature, and then we spent some time practicing what we just learned.